Often, mistakes arise when we try to fit a neat story onto a messy situation. Mathematical thinking teaches you to distinguish between structure and decoration, and to question what a situation truly implies. Begin by identifying quantities, defining them clearly, and considering how they might change together. Next, test your assumptions by imagining extreme cases and checking if the logic holds. When an argument feels persuasive, translate it into relationships that can be verified, not into slogans that cannot. Good reasoning acknowledges uncertainty, treating knowledge as partial and subject to revision rather than absolute. This approach values clarity over cleverness and precision over confident guessing. It also promotes approximation, as rough answers can reveal direction and scale without unnecessary detail. The aim is not complex calculations, but fewer errors in judgment and better questions at the outset. For a deeper toolkit, read How Not to Be Wrong by Jordan Ellenberg and subscribe for more ways to think clearly. Many models assume a constant rate of change, but that assumption quietly fails in bounded systems. When a quantity cannot rise past a limit, the same increase now cannot mean the same increase later. Linear thinking treats each extra unit as identical, even when context changes the effect. Nonlinear thinking asks how the slope changes with the level, and whether feedback reverses direction. A straight line can fit local data while giving nonsense outside the range where it was observed. Percentages near 0 behave differently than percentages near 100, so predictions need constraints. Real decisions require checking whether more of something helps, harms, or switches between them. The safest habit is to sketch the curve shape and list the limits before trusting a formula. When relationships bend, policies based on straight lines can overshoot, undershoot, or miss the target completely. Treat linear rules as temporary tools and retest them whenever the scale or baseline shifts. Data often reveals only what survived a process, not what entered it, so conclusions can be misleading. Selection effects can hide failures, and the missing cases usually carry the most crucial information. To check this, ask what outcomes would remove observations from the dataset you are using. When survival and outcomes are related, the remaining sample will not represent the entire population. This is why the absence of evidence is weak when the evidence had a way to disappear. Mathematically, you should treat the selection rule as part of the system, not as background noise. Setting some probabilities to 0 can reveal which explanations make sense and which rely on coincidence. Once the filter is visible, you can decide where protection, effort, or measurement actually matters. The lesson is to look for the holes you cannot see, not just the marks you can count. Being less wrong starts with asking which stories fit the data and which also explain why data is missing. What you should believe changes only after you combine evidence with what was plausible beforehand. Probability is not just about random events, it is a method for assessing confidence across competing hypotheses. Even a small probability event can still be the best explanation when every alternative is even less likely. This requires comparing explanations, not just measuring one number in isolation. In practice, you update by considering how expected the evidence was under each candidate explanation. Priors can be incorrect, but ignoring them can lead to certainty from thin evidence and overreaction. The goal is a disciplined shift in belief, not a dramatic change based on a single new fact. When someone claims a result is obvious, ask what assumptions were used and what other models were rejected. Better inference comes from transparent comparison, calibrated doubt, and a willingness to revise when new facts appear. Practice these belief updating habits to avoid being misled by unlikely claims presented as certainty. Correlation measures how closely points cluster around a line, but it does not explain why they cluster. A high correlation can arise from shared causes, selection, or definitions, not just direct influence. Regression describes the typical value of one quantity given another, and predictions tend to be closer to the average. This is not a matter of morality, but of geometry. Extreme values usually mix signal with noise. When you predict from one measurement, expect the prediction to be less extreme than the measurement itself. Confusing regression with change can lead to false stories about improvement, decline, or hidden forces. The shapes of scatter plots matter more than a single summary statistic alone. Always ask which direction of prediction you are making and whether the relationship is stable across groups. Treat every fit as a conditional statement. valid only under the data-generating process you believe. Using regression well means tracking uncertainty, checking residual patterns, and refusing to treat prediction as proof. Decisions under uncertainty require combining outcomes with their probabilities, not focusing on one possibility. Expected value summarizes the average result across repeated choices, but people also care about risk and regret. Utility translates different kinds of costs and benefits into one scale, allowing for the comparison of trade-offs. Changing the utility scale changes the best choice, as the best choice depends on what you value. The key is consistency. If you can rank outcomes, you can model choices without pretending the model is perfect. This approach forces you to name what you fear, what you accept, and what probability you can live with. It also shows why the best strategy often allows a small chance of a bad outcome. Trying to eliminate all risk can create guaranteed costs that outweigh the rare loss you are avoiding. When a slogan promises zero downside, translate it into utilities and check whether the implied trade-off is real. Expected utility thinking keeps choices grounded as it combines chance, cost, and preference in one coherent calculation. Some questions do not have a single collective answer, even when each person has clear preferences. Majority rule can produce cycles where each option loses to another, depending on how choices are presented. Poll results can be true and still misleading when the options hide internal splits within the same percentage. When preferences do not form a coherent direction, talk of one public will become empty. The practical response is to demand clearer questions, richer alternatives, and transparency about what is being compared. Mathematical thinking does not remove disagreement, but can expose where the disagreement cannot be summarized. That exposure reduces manipulation because it limits which headlines can claim a mandate. Across every topic, the guiding move is the same: define the objects, test assumptions, and look for missing structure. You do not need advanced formulas to do this, only habits that resist shortcuts and reward careful definitions. Subscribe for more tools that sharpen these habits and help you spot bad reasoning before it steers your choices.